All right, welcome. We are here looking at Unit 2, and we're in Lesson 1. This part is Section 2 of Lesson 1 called Building Boxes. And this one takes a lot of materials, and so it's a little bit easier if we just show it to you here in this video. So please follow along with the video and fill out some information in your workbook as we go. It's asking us to construct an open top box from a sheet of paper by cutting out a square from each corner and then folding up the sides. So I have a regular standard piece of paper here, and if you don't already know the dimensions of a piece of paper, a standard piece of paper, it's 11 inches on the long side and 8.5 inches on the short side. So we're going to keep using these dimensions throughout this activity and actually throughout this unit. So this is a good video to maybe come back to at different points in the unit. So it's asking us now to cut a square from each side of different lengths, and we're going to start by cutting a 1-inch square from each corner. Now I already have 3 of those corners marked here, but just so you can kind of see that process, I'm just marking 1 inch on each corner, and it's a 1-inch square, so it'll be 1 inch along each side, and then we're just going to cut out those 4 corners. Once we have those 4 corners cut out, I'm not going to show you every single step of this, but I have one here that is already cut out. So each of those 4 corners is already cut out here. And you can tell each of them is a 1-inch portion. Then by folding up the sides like this and just using a small piece of tape, we can tape these corners. And once we have all 4 of them taped, you can see that it forms that open topped box that we were talking about that was in our instructions. So we have formed an open top box from a standard piece of paper by cutting a square out of each side. And when we have all 4 of these sides taped, we're going to find the volume of this box. All right, so how much stuff could we put in the inside of this box in order to fill up this volume, to calculate what the volume of this open top box is. So when we think about this, about what are the dimensions of this box, we know that the height is 1 inch because that's what we cut out of the side there. So the height is 1 inch tall. It's the same as whatever the side length is that we cut out here. And then the length of paper that was 11 inches. We had those 11 inches of length here, but we cut out 1 inch from this dimension and 1 inch from this side. So instead of it being 11 inches, once we have that part folded up and cut out, we actually have 11 minus 2 inches, 1 from each side. So this box has a length now of 9 inches. All right, so if you need to write yourself a little note, it started as 11 inches. We subtracted 2 1-inch squares to equal 9. And we can think about the same thing for the width of the box. It was 8.5 inches of paper. From that 8.5 inches, we cut off 1 inch from this side and 1 inch from this side to have these little notches out. And so we had 8.5 inches minus 2 1-inch squares on each side. And so we're left with 6.5 inches. And so we have these dimensions, and to find the volume of the box, you may remember this from geometry. It is length times width times height to find the volume of a box. And so we need to know what 9 times 6.5 is. And my calculator is telling me that 9 times 6.5 times 1 is 58.5. So this box would hold a volume of 58.5 cubic inches. Now, we can also cut out different sizes of corners, and I'm about to hit pause on this video and show you what these will look like, but I'll show them to you flat. Each one of these started off as a full standard sheet of paper, 8.5 by 11. And you can see that I've cut out different size squares from each corner, and I did them in some different colored paper so we can see what the result is. I'm going to hit pause on my video, and I'm going to tape these sides up so we can see what those dimensions are when we have cut out 2-inch corners, 3-inch corners, and 4-inch corners. Some interesting things might happen. All right, hang on just a second, and we will be right back. And through the magic of video and the pause button, I have now constructed those 3 boxes from our different pieces of paper that we had. Again, one of them was a 2-inch, one I cut out 3-inch squares, and the last one I cut out 4-inch squares. And so I have these very different shaped boxes. You can kind of see that they're all pretty different shapes that are going on here. And what's kind of neat is, like, you know, if I wanted to, I could kind of stack them all up, and all together you can kind of see that they all nest inside each other. But we have some very different shapes going on here. We already calculated the volume of the orange one, so let's take a look at the volume here of our pink one. This is the one that I cut out a 2-inch square, so we already know that it has a 2-inch height to the box because that's the same match as the length of the square that we had cut out. And then for the length that we had, it started again as, let's see, an 11-inch span. We cut out 2-inch squares, one from each side. Remember, that length comes from off both sides there. And so when we cut off those 2-inch squares, we're left with a 7-inch length. And if we really wanted to, we could verify that, boom, with our ruler, and we're showing clearly that we have a 7-inch length going on here. So our length is 7 inches. Again, that's 11 minus 2 times 2, because that's what we cut off. And the width that we have started again at 8.5 inches. We cut off 2 2-inch portions, and that left us with 4.5 inches left. It's a-okay to always have a little bit more information about like how you came up with that calculation. So if you want to be writing down that information that we have like that. And when I multiply this out using my handy dandy calculator of any kind that you have, this is simple multiplication. So I'm doing 7 times 4.5 times 2, and I find out that this has a volume of 63. Now that's pretty surprising. A lot of students think that if we have the same starting piece of paper, we should have the same volume of the box at the end. But we're seeing now that our volume is starting to change depending on our dimensions. Let's give it a try with our 3-inch tall box. So if we cut out a 3-inch square from each corner, it's going to have a 3-inch height to it. Our length, and I can do it even without looking at what I've drawn on here, is going to be 11 minus 2 3-inch portions, so 11 minus 6, which would give us 5 inches. There we go. And for our width, we'd have 8.5 minus 2 3-inch sections. 8.5 minus 6 is a nice solid 2.5. And now to find our volume, length times width times height, 5 times 2.5 times 3 tells me that I have a 37.5 cubic inch box. There's our green guy. That's what could fit inside there. And last but not least, the 4-incher. Here's a nice visual of it. It's a tall, super skinny box. So its height is again going to match the 4 inches. We have now cut off 2 4-inch sections from each side. I'm already writing that it's an 8. So we would have our 3 inches. There's a nice pattern going on there, talking about patterns from our first unit. And our 8.5 inches minus 2 4-inch sections leaves us with just a 1/2 inch of width. So that's all that this is wide right here, is just a 1/2 inch wide for this box that we have. So we could put some stuff in there, but I wonder how much that's going to be. 3 times 0.5 times 4. It's only 6 cubic inches. So we can see we have some big variety going on here. And at first the numbers seem to be growing in volume, and then it looks like they start shrinking in volume. All right, so we're going to skip down really quickly here to the next section, because you're going to complete this next section on your own or with a partner nearby. And it's asking in number 2 about how we could write an expression for the volume of this box. We've already set up here every single time the height matched whatever is the length that we cut out. So if we cut out any length x, which this is now saying we can make it any variable, because it could be any number in between here too. We could cut out 1.5 inches or 3.5 inches. And there's a limit to how much we could cut out. That's going to be for you to discover. But we know that the height always matched whatever our side cutout was. And then our length, we were saying, always started as 11, because it was an 11 by 8.5 inch paper to begin with. And we always subtracted off 2 times whatever x was that we cut off. So that's why I was purposely writing it up here, to help you out with that kind of dimension of how we calculated that. And you probably already ahead of me. The width is right from the same equations we were working with up here. The width of the paper started at 8.5, and we always subtracted 2 x's from it, one from the top and one from the bottom. So we have a nice expression to begin with, but I'm going to leave it to you to figure out how you could find what is the largest possible volume of box that we could get out of this 8.5 by 11 piece of paper, and continuing on about what are our limitations for what's the least amount we could cut out and still end up with a box, and what's the most amount we could cut out and still end up with a box. You're probably already guessing what that might be, because this guy got really small. We have to at least have some side here, so you might want to think about what that limitation could be. All right, thanks for watching.